Hello students, welcome to today's lecture on theory of machines. Today we'll be discussing about the types of constraint motion. So in the last classes we discussed about the kinematic pairs, we defined kinematic pairs and we saw the classification of kinematic pairs. And we said that two links or elements of a machine, when in contact with each other, they are said to form a kinematic pair. But we also said that there should be a relative motion between the two links which are forming the kinematic pair, and that relative motion should be a constraint motion or a definite motion or a predictable motion. Constraint motion means the motion which we can predict, or it is in a definite direction. So we defined the constraint motion also in the last class, that the motion in a definite direction, or the motion that can be predicted, or the motion in a single direction or in one direction is known as a constraint motion. Right? So today we are going to see what are the types of constraint motion. So types of constraint motion. So basically we have three types of constraint motion. The first one is completely constrained motion. So in completely constrained motion, the motion between the elements of a pair should be in one direction, right? Or it should be in a definite direction, irrespective of the direction of the force applied, right? So if the motion between the elements of a kinematic pair is in a definite direction, irrespective of the direction of the force applied, then this type of motion is known as completely constrained motion. So let me write down this thing. The motion between the links of a kinematic pair is in one direction or definite direction, irrespective of the direction of force applied. Then this type of motion is known as a completely constrained motion, right? So for example, we have seen earlier the motion of a square bar inside a square hole, right? So we have seen this earlier. Let me show you with this diagram. So this is how this thing looks like. So you can see that there is a square bar which is placed inside the square hole of a square block, right? So this rod will have only reciprocating motion inside the square hole, irrespective of the direction of the force applied, right? In whatever direction if we try to apply the force, it can have motion only in the to and fro direction, or it can have only the reciprocating motion. It cannot have the rotary motion, right? So let us see this by an animation. So you can see here in the animation that this square bar can have only the sliding motion or the reciprocating motion inside the square hole of the square block, right? So I hope this is clear. Second type of constraint motion that we have is incompletely constrained motion, right? So the motion between the links of a kinematic pair is known as incompletely constrained motion if the motion between the links of a kinematic pair can take place in more than one direction, right? In other words, in incompletely constrained motion, the elements of the kinematic pair can have more than one type of motion with respect to each other, and the type of motion between the links of a kinematic pair will depend upon the direction of the externally applied force, right? So let me write down this first. If a link of a kinematic pair can have more than one type of motion with respect to each other, and the type of motion depends on the direction of the externally applied force, then this type of motion is known as incompletely constrained motion. So why this is incomplete constrained motion? Because we will not be able to predict the exact motion of a kinematic link with respect to the other, because it can have motion in more than one direction, right? And the type of motion that one of the link will have with respect to the other link will actually be depending upon the direction of the externally applied force. Let us take an example of a round bar which is placed inside the square block with a circular hole. So this round bar is free to have a rotary motion as well as a reciprocating motion, right? And the type of motion of the round bar will be actually depending upon the direction of the force that will be applied. If we are applying a tangential force, then it will rotate, and if we are applying a push and pull force, then it will be having a reciprocating motion, right? So depending on the direction of the externally applied force, the round bar will be having either reciprocating or rotary motion inside the circular hole of the square block, right? So let us see this by an animation. you can see here this round bar can have reciprocating as well as rotary motion inside the circular hole of the square block, right? So this is an example of incompletely constrained motion. The motion of a circular shaft in a circular hole, right? So this is about the incompletely constrained motion. The third type of constrained motion that we have is successfully constrained motion. So what does this successfully constrained motion means is that suppose if the motion between the links of a kinematic pair is incompletely constrained motion, and we are making that motion as completely constrained motion by some external means, then that type of motion will be known as successfully constrained motion, right? So what does this mean? That means if the motion between the links of a kinematic pair is made completely constrained by some external means, then that type of motion will be known as successfully constrained motion, right? So let me write this down. If the motion between the links of a kinematic pair is not completely constrained by itself, but is made completely constrained by some external means, then this type of motion is known as successfully constrained motion. Right? So what do we mean to say? That the motion actually is not completely constrained, or basically it is an incompletely constrained motion, but we are making it as a completely constrained motion by applying some external means, right? So the example that we can cite here is like the previous example of incompletely constrained motion. We had a circular shaft inside a circular hole of a square block. It was free to either reciprocate or rotate depending upon the type of externally applied force. But if we apply two collars at the two ends of the circular hole, then due to these collars, the reciprocating motion of the circular shaft will be restricted. And now it can have only the rotary motion, right? So this is how, by the application of the collars or by the application of some external means, we have made the incompletely constrained motion to completely constrained motion, right? So this is one of the example of successfully constrained motion. Let us see this by an animation. So here you can see by the application of the collars, now the motion of the circular shaft is restricted to only a rotary motion, right? So the example is the motion of a circular shaft in a circular hole with corners at both ends. There is one more very good example, that is of footstep bearing. This footstep bearing you might have seen when you have studied this machine drawing. Generally, they teach how to draw the assembly of footstep bearing. So, let me show you a picture of footstep bearing. So, this is how the footstep bearing looks like. Now, in this footstep bearing, the shaft may rotate in the bearing and it may also move upwards. In that case, the motion of the shaft inside the bearing is incomplete constraint motion. But if we apply this load on the shaft, then the shaft cannot move upwards, or it cannot have the upward movement. So then the motion of the shaft inside the footstep bearing will be completely constrained, or it becomes completely constrained, right? So this motion of the circular shaft inside the footstep bearing has been obtained by some other means, that is by placing the load on the shaft. So this type of motion is known as successfully constrained motion, in which we attain the completely constrained motion by some external means, right? Another example of successfully constrained motion are the motion of IC engine valves. So basically they are kept on their seat by the application of the spring, right? And also the piston reciprocating inside the engine cylinder is an example of successfully constrained motion, right? So this is about the type of constrained motion. So we saw that constrained motion is basically of three types. Completely constrained motion, in which the motion between the links of a kinematic pair is only in one definite direction. Similarly, incomplete constrained motion, if a kinematic link can have more than one motion or more than one type of motion with respect to the other, then it will be a incompletely constrained motion. And if we are making this incomplete constrained motion, or we are converting this incompletely constrained motion to a completely constrained motion with the application of some external means, then this is known as successfully constrained motion, right? So this is all about the type of constrained motion. I hope you have understood the classification of the constrained motion. And this is very important to understand, because whatever mechanism that we are trying to design or output motion that we are desiring should be a constrained motion. We are making a machine to do a particular type of work, or we are designing a mechanism so that we get a particular type of motion at the output. So the motion at the output should be definite, and that means we should be able to predict the motion at the output. What I mean to say here is that whatever input motion we are giving to a particular link, we should be able to predict the motion that we'll get at the output. Then only we'll be able to design the mechanism effectively, right? So the relative motion between the links of a kinematic pair should be either completely constrained motion or successfully constrained motion, right? So I hope you have understood this concept of constrained motion. So this is all for today. Thank you very much.